Today we will take up a rigid plane frame problem for the analysis. Because as per your syllabus, you have analysis of stresses, analysis of beams and rigid plane frame. Already we have finished analysis of stresses and beams. Now we will take up this last time, that is rigid plane frame problem. Here I have considered a rigid plane frame. So let us analyze this rigid plane frame by this matrix approach. As usual, the first step, we have to identify the global and local coordinate system. The local coordinate system corresponding to unknown to be determined at the ends of the members. I told you we are selecting only the unknowns as the moments at the ends of the member. Each is a beam member here, both column and beam. We are treating it as one-dimensional beam member or flexural member. So the independent end forces are moments. The shears, we can automatically determine by equations of equilibrium when once we know the end moments at ends of any member. Because shear at one end can be obtained by taking moment at the other end. Because end moments are known, that shear can be determined. Other shear force can be determined by equating all vertical forces equal to 0. So the independent unknown member forces, member end forces are only the moments. And that we have to determine only at the ends of the member, that we define as the local coordinate system. So the local coordinate system corresponding to the end moments, whose sign as per sign convention, the clockwise moments we have taken as positive and we take in that direction. We call this as member 1, this as member 2, this as member 3. PM1 and PM2 are the end moments of the member 1, and PM3, PM4 are the end moments of the second member. PM5 and PM6 are the end moments of the third member. So therefore, the unknown member forces are PM1, PM2, PM3, PM4, PM5, PM6. I'll write transpose. It says is here in the book. So this is a 6.1 matrix. So this is the unknown which we have to determine during the analysis. That is member end forces. And the global coordinates are corresponding to the displacements which we have to determine in global coordinates or system coordinates. Actually, this is the frame wherein in plane frames we have at each node 3 types of displacements: horizontal, vertical, that is 2 translation, and a rotation about an axis normal to the plane. So here at the joint A, no displacement is possible. All displacements are 0 in global coordinate system. So here also joint D, no displacement is possible. Here, the displacements are possible because it is a continuous end. So first I will mark the rotations D1, D2, that is the rotation at B, rotation at C, that's the unknown. Then members are axially rigid. So this vertical displacement, it is possible at the joint B. If it moves up or down, then other end of the member AB, that is A, should also move up or down, but A cannot move, so this also cannot move. Because I told you when members are axially rigid, it should move as a rigid body motion. Bodily it should move. So when it moves, when it is not possible to move, the vertical displacement here also should be 0. On same argument, for member CD also, this end, though it can move up or down, the other end of the member CD, whether it D, should also move up or down, which is not possible. So this is also not possible. So this is also 0. Then coming to the horizontal displacement at B and C, this B, it can move horizontally. Of course, here load is given acting from left to right, so it has to move from left to right. So if it is a load is given from right to left, it has to move from right to left. If load is given from both sides, left to right as well as right to left, then whichever side larger load is there, that side it will move. Like that you can decide about this horizontal movement. Of course, B can move horizontally in the direction of the load. So that is, it can move like this. So let it move here up to here, say delta. So this cannot move, so it can move like this. Here it cannot move. Then, since this member is axially rigid, so whatever this end moves, this end also should move by same amount. Bodily it has to move. That's called rigid body motion. No, there won't be any deformation within the member. Bodily the member moves like that, that's all. As it is, its length will not alter. So here, this end also can move. Whereas here in the vertical member, this other end was not possible, so that's why I made it 0. Now it is possible, so this end also should move by same amount. Body it has to move, because there won't be any contraction or elongation. So the movement here is not different from the movement here. So this can move like that. So unknown displacements, because of the given external possible displacements are D1, D2 and this is D3 or delta, whatever it is, D3. So the ds is equal to D1, D2, D3. That is the 3 by 1 matrix. This is another thing we have to determine. This is called global coordinate. This is local coordinates. So in the local coordinate system, we have to determine member and forces. In global coordinate system, we have to indicate whatever displacements which we have to determine. After marking the possible displacement at each joint or each node and removing the impossible displacement because of the distance at the support. After removing whatever is available, that's called kinematic indeterminacy. Kinematic indeterminacy of this is 3, and that is what we have to determine. Unknown displacement, unknown member and forces. This is the first step. Then we have to find out the forces corresponding to this unknown displacement in global coordinate. That forces should be acting at the nodes only. But here, loads are given at the members. We have to find equivalent end forces or equivalent joint or node forces. How to find the equivalent joint forces? Don't allow any displacement, assume each ends of the members to be fixed. Like this, whatever node is there on the member, due to that load, whatever reactions which are going to develop, you determine. This of course from your undergraduate level, you have already determined fixed beam analysis. So this beam BC is subjected to a load of 25 kilonewton meter and span is 6 meters. Therefore, the reactions here, since it is symmetric, it is total load divided by 2. That is 25 into 6, 150 by 2. That is 75 kilonewtons, 75 kilonewtons. And the moment here, it is in the anti-clockwise direction because applied moment is due to load is clockwise, resisting has to be anti-clockwise. So this moment will be Wl squared by 12, where W is the intensity of the load. So that is 25 into 6 squared by 12, that is also 75. Since the resisting is anti-clockwise, as per our notation, it is minus 75. So here it is plus 75. On same lines for this also, this number. So now we got equivalent, not equivalent, joint end reactions. So this reaction, you have to reverse its sign. As I told you in beam and beam problem. So here also we have to reverse its direction. That will be the equivalent joint load, and that equivalent joint load corresponding to these degrees of freedom, D1 and D2, D3, we have to take it as global load matrix. So that is another exercise you have to do in this first step. So here also you have, here it is clockwise because applied is anti-clockwise. Here applied is clockwise, resisting is anti-clockwise. So this is also Wn squared by 12. So that is 25 into 6 squared by 12. That is also 75. This is plus 75. This is minus 75. Likewise, reaction, here it is like this, here also it is like this, that is 75, 75. Because applied load is in this direction, reaction has to be in this direction. Now, therefore, your PMF, that is member end actions, member end moments corresponding to these local coordinates, member end moments corresponding to local coordinates are minus 75, 75, minus 75, plus 75, then and in this member no load is there, so it is 0, 0. This PMF matrix, as you have seen in beam, is the member end actions due to given load in local corresponding to local coordinate system. Local coordinate system are this PM to P1 to PMX. So corresponding to that, these are the loads. This is transpose. So it is also a 6 by 1 matrix. This is used in the last step where we are determining the member end forces at various ends of the member. Then PS is equal to corresponding to this forces equivalent joint member end action corresponding to these coordinates. So corresponding to D1 coordinate, here it is plus 75, here it is minus 75. So corresponding to D1, which is at the joint B. So the total net force is 0, 75 minus 75. So it is 0. Corresponding to D1, force is 0. Corresponding to D2, here, fixed end action, of course, here it is 0, 0 in the other. So here it is plus 75, here it is 0, it is plus 75. So this is plus 75 moment. Now corresponding to D3, this is the difference from the B problem. B problem, we were not having this. You only in settlemental support, that is sway. This is called sway. This translation motion, we call it as sway. Translatory motion either perpendicular to vertical member or horizontal member. Both we call it as sway. This is called horizontal sway, that is called vertical sway. Here vertical sway is not there, only horizontal sway. That is only columns are undergoing sway. Net it is a sway. But actually there is no difference between sway and non-sway analysis, except here we have to consider. And here, one more thing I forgot. While taking PS, we have to reverse the sign, PJ minus PMF. So here we have to reverse its sign. Here NA 0, don't reverse its sign. 75 we have to reverse its sign. Now, coming to this D3, the force. Here D3 this is the force, reaction, 75. That is corresponds to your D3. So it is 75 acting here, right? So this 75 is the force. It is acting opposite to that, minus 75. So that side we have to reverse it. So it has to be plus 75. Because here we don't have any horizontal loop. So this is that EMF matrix. So this much work you have to do in your first step. So that is, you have to identify what all the things you have to determine during analysis. You have to determine forces, then forces, that is independent then forces, that is moment, as well as displacements. That is the total mass. Next, second step. Second step is your member stiffness matrix. Member stiffness matrix. KM. Member. For all the members, you have to assemble the stiffness matrix. You know, each is a B member. So treating end moments, that is unknown member and forces, we have selected. So the stiffness matrix is given by 2 EL by N, 2, 1, 1, 2. That is the member stiffness matrix corresponding to the 2 end moments. It has to be a 2 by 2 matrix because there are 2 end moments for each member. Corresponding to this, it is first row. Corresponding to this, it is second row. Like that. So therefore, your KM1 member stiffness matrix for the element 1, it is equal to 2 EL by L. EL value is 2 EL. That is 2 into 2 EI, it is 4 EI by L. L is 6 meters. So it is 2, 1, 1, 2. So that is equal to 2 EI by 3, 2, 1, 1, 2. So next KM2. KM2 is also having same EI and span. So this is equal to KM2. KM1 is equal to KM2. Next, KM3, member 3. The stiffness matrix is equal to, this is the member 3. EI is EI, L is 3. So it is 2 EI by 3, 2, 1, 1, 2. That's all. Therefore, the total member stiffness matrices, we assemble it in matrix form that is equal to 2, 1, 1, 2, then 2, 1, 1, 2, then 2, 1, 1, 2. So diagonally you write this stiffness matrix for the entire structure like this. This is it is 6 by 6 matrix totally for the entire structure. The member stiffness matrix is given by this. So next, third step, you have to find the transformation matrix. Transformation matrix, that is, whatever member stiffness matrix which you have determined, that you have to transfer to global coordinate system, because you have to determine global displacement. So the stiffness matrix also you have to convert it into global stiffness matrix, so that you can use that force displacement relationship PS is equal to KS ds. From that you can evaluate ds. That's all the job. ds can be determined. Then finally you can determine PM also. That's the only step. 7 steps I have already told. Same 7 steps here also you have to follow. So transformation matrix, how you are determining? So you have to apply unit displacement along each of the global coordinates, one at a time. Along each of the global coordinate system, you have to apply unit displacement and find the corresponding displacements corresponding to local coordinate which you have selected. So that means there are 3 global coordinate systems. You have to apply 3 unit forces. One first, d1 equals 1. You have to apply, then you have to apply unit displacement along second coordinate system, second global coordinate system. Then you have to apply unit displacement corresponding to third coordinate system, global coordinate system, that is this 1, d3, here also d3, both are equal, d3 equals 1, d3 equals 1, you have to apply. So then you have to find corresponding local coordinate moments. Local coordinate moments. That's the job. When you give a displacement like this, so this will displace like that. You have to, by giving this displacement, all other nodes, you have to restrain. So here you have to give like this, like this. 1, 1. So 1, 1. Corresponding to PM3, PM2, displacement is 1, 1. Here, no displacement, because you have to restrain, I told. Here, no displacement. Here, no displacement, because all other points you have to fix, other than wherever you are giving unit displacement. So now, this is the first column of this rotation matrix. That's a very simple calculation. So first column corresponding to PM1, it is 0 displacement. Corresponding to PM2, it is 1. Corresponding to PM3, it is 1. Corresponding to PM4, 0. PM5, 0. PM6, 0. So this is that first column of that rotation. Likewise, when you give a unit displacement here, so and this you are fixing, it will displace like that. It has to displace like that. Here it is 1, here it is 1. At all other points it is 0. So this is 0, this is 0, here 0, here it is 1, here also 1, here it is 0. So naturally the second column here 0, 0, 0, 1, 1, 0. Second column. Now here it is due to sway. How the displacement occurs? See here displacement is there because this has swayed like that actually. So this has gone like that, this has gone. Originally it was straight, now it has moved clockwise. Well, you know, as per our in slope deflection method, sign convention is if you have a clockwise rotation of the original chord, it will be sway is negative, sway moment. Otherwise, sway moment is positive. So here, sway moment or sway displacement. If delta is taken as negative if it results in clockwise rotation, whereas force, that is moment, it is positive if it is clockwise. Sway moment, it is opposite to that. That you have to remember. So here, what is this sway? This displacement, because we have to find displacement corresponding to PM, that is rotation. What is the rotation here? So it is tan theta, approximately. Theta is very, very small, so tan theta you can take it as theta itself, that is rotation itself. So here tan theta is opposite side, 1 divided by adjacent side, 6. So this rotation is minus 1 by 6. Observe, this is the difference to determine the displacement. So here also minus 1 by 6. Why minus? It is clockwise movement. But don't take clockwise movement is positive, so clockwise rotation also positive. It is difference is there between displacement and this in sway. Likewise here, when this has moved like that, so it has moved like this, then it is results in clockwise rotation of the chord. So here also on same line, this will be tan theta. Tan theta is 1 divided by 3 here. So it is minus, so it is minus 1 by 3. Here also it is minus 1 by 3. Here of course it is 0, 0 because beam has not undergone any rotation because of this sway. Only the column members has undergone sway. So due to that sway, whatever rotation they will take, and that is corresponding to your local coordinates. So now you can write corresponding to this what is the third column. So corresponding to PM1, PM2 and all. PM1 it is minus 1 by 6, PM2 minus 1 by 6, PM3, PM4 it is 0, PM5 it is minus 1 by 3, here also minus 1 by 3. Space. So the rotation matrix now, finally, you get first column 0, 1, 1, 0, 0, 0, then 3 zeros, 1, 1, 0, then minus 1 by 6, minus 1 by 6, 0, 0, minus 1 by 3, minus 1 by 3. So it is a 6 by 3 matrix. 3 corresponding to 3 global coordinates, whatever displacements, that is 6 in the local coordinates. Next, fourth step, global stiffness matrix. KS. You know from principle of contact gradients, KS is given by RT, that is transpose of rotation matrix into Km into R. So therefore, this, here R is 6 by 3, RT is 3 by 6. RT will be 3 by 6. We have to change rows to column, column to row. Km is 6 by 6 matrix, R is 6 by 3 matrix. So the multiplication is possible because column here equals row, here column equal to row. Ultimately, this KS will be 3 by 3 naturally because global coordinate is 3 by 1. Here you have to get 3 by 3 global matrix. So whatever what you are doing is perfect. That you can check on. So therefore, this KS is equal to RT, that is 0, 1, 1, 3 zeros, 0, 3 zeros, 1, 1, 0, then minus 1 by 6, minus 1 by 6, 0, 0, minus 1 by 3, minus 1 by 3. This is that 3 by 6 matrix of RT. Km, here 2 here by 3, I will take it outside. I will get 2, 1, 1, 2, 0, 0, 0, 0, 0, 0. Then 2, 1, 1, 2, 0, 0, 0, 0, 2, 1, 1, 2. This is Km matrix 6 by 6. Then R. R is 6 by 3 matrix 0, 1, 1, 0, 0, 0, 3 zeros, 1, 1, 0, minus 1 by 6, minus 1 by 6, 0, 0, minus 1 by 3, minus 1 by 3. So these are the 3 matrices, RT, Km, R. So this, if you finish, so I have it set. So Km, Ks will be, finally, you will get EI by 3 into 8, 2, minus 1, then of course here it is 2 minus 1, then 8, minus 2, minus 2, then 5 by 3. This is a 3 by 3 matrix, KF, finally. So that is your fourth step. Then fifth step is solution of equation, formation of equation, formation of equations. So that is we have the force displacement relationship in global coordinates is given by Ps is equal to Ks ds. So Ps is equal to, we have determined in the first step, that is load corresponding to global coordinate system, that is 0, minus 75, 75, then Ks here by 3, 8, 2, minus 1, 8, minus 2, minus 2, 3 by 3. This is the Ks. ds, what we have to determine, d1, d2, d3. So, this equation either can solve the simultaneous equation, or you can invert this Ks matrix, multiplied by Ps, you will get the displacement. Whichever is easy, or the computer program what you are writing, if you have a solution equation solver, you can use that. Otherwise, matrix, MATLAB, you just invert it. So that is your next step. Sixth step is to find unknown displacements. To find unknown displacements. That is, I told you in the first step itself, you have to determine unknown displacement corresponding to global coordinates, because loads will be in the global coordinate system, acting load. It is always in the global system you have to take, you have to resolve all the loads in the global system, and the displacement also should be in the direction of the loads, that is global direction. That you have to determine. Then members, the forces, you have to remember internal forces developed within the member, that you have to determine correspond to local coordinate. Analysis means you have to determine internal member forces developed as well as displacements at various joints. That is how we define the analysis. Along with, of course, support reaction. Reactions automatically you will get it. You can find from the static situations, nothing other than. So this is the unknown displacements, ds. So solving the equations in step 5, you will get d1, d2, d3. As I have it here, the solution 1 over ei into 17.65, then 5.51, then 152.2, 2.2. And of course, units, whatever EI unit is there, it will take care about that, millimeter, whatever it is. Then last step, that is 7th step, because I told you there are 7 steps for the analysis, whether it is classical approach or finite element approach, both similar. In the finite element approach, the difference is only in the first 4 steps, the first 3 steps. Others are all same as classical method. Global formation and solutions, formation of equation, solution, and finding the final invariant forces. So only that remaining 2-3 steps that you have to, in the finite element method, you are doing in a separate way. That is, you are determining the member stiffness matrix, that is, development of stiffness of member stiffness matrix in local coordinate system. So here I told local coordinate system, there we adopt what is known as natural coordinate system. That's also local coordinate system only. So in the natural coordinate system, we determine Km, and for the corresponding rotation matrix, we will determine, and we arrive at the global displacement. Except that change, that the element property and element equation formation, no other change is there between this classical approach and finite element approach. That's why in the syllabus also they have told only analysis of plane frame structures only, that to frame structures, one-dimensional structures, no two-dimensional problem. It's very simple, straightforward syllabus. No complication, nothing. All only frame structures. Beam, plane frame, trap. All are frame structures. It's a very simple process by both approach. Problems are also same. Only difference already I have told. Where it lies. Only formation of element property, that is stiffness in element coordinate. That we are determining. Here local coordinate, here natural coordinate system. That we have to determine what is natural coordinate system. And that of course I will say continue in the same class. So after this, last step to find current steps, to find unknown member-length forces. Member-length forces. The unknown member-length forces are PM1, PM2, PM3, PM4. So already I have given formula. PM member-length forces is given by PMF. That is, if there is a member load, then the corresponding PMFs, whatever you have determined, due to that member and reaction, that you have to add it to these forces corresponding to unknown displacements. That is, PMF plus Km into Dm. Stiffness matrix in local coordinate, displacement in local coordinate. And of course, that is equal to PMF plus this Km. Dm is from your principle of contractilities, which I already have told. Dm is R into ds, that is transformation matrix into displacement in global coordinates, which you have determined. Transformation matrix also you know now. Km is already known. PMF, no. And everything is known, you can find is P. That's member N. That's all the problem. Therefore, your PM, that is PM1, PM2, PM3, PM4, PM5, PM6. It is a 6 by 1 matrix that is equal to PMF corresponding to that 6 distinct member end actions have 75, 75, minus 75, 75, and 0, 0. Then plus Km is 2E by 3, 2, 1, 1, 2, all the rest. 0, 0, 0, 2, 1, 1, 2, 0, 0. This is that PM, which is a 6 by 6 matrix, and multiplied by R. R is 0, 1, 1, 0, 0, 0, 3 zeros, 1, 1, 0, and minus 1 by 6, minus 1 by 6, 3. Then d as just now we have determined, that is equal to 1 over EI into 17.65, 5.51, then 152.2. So this EI and this EI, you can take it out. So you can multiply this. This is 6 by 3. This is 3 by 1. So multiplication is possible. You just see here column is equal to row. Result will be 6 by 1. Then this is 6 by 6. This column and that is row is 6. So resulting will be 6 by 1. So this is also 6 by 1. 6 by 1 plus 6 by 1. They are of same order. You can add each results in your payment. So the final result, of course, I have. So you can cross check. So final result is you are going to get this member and actions as minus 114, 47.8, minus 47.8, 94.1, minus 94.1, then minus 97.8. That is the result. Final member and force. Whatever we have identified in the first step, the member and unknown member and forces and unknown displacements, that we were able to solve by this classical approach. So same procedure we have followed in the beam analysis as well as settlement also. Beam analysis beams are non-sway, but due to settlement it is sway, but sway is known. Settlement value they will give, that's why sway is known there, delta was known. That's why this non-sway we treated as non-sway beams. So sway frame. If frame is non-sway, then delta term will not come into picture. That extra exercise of finding rotation, that is after finding tan theta, that is not there. Only rotation in the affected members that you have to determine. That's all. So I hope I have covered all the aspects of the syllabus of Unit 1 and 2. That is classical approach. It is complete. So Unit 3 and 4 also I will take up now. So 3, 4 I will try to finish basic concepts I will touch, which is nothing. 3 and 4. 3 and 4 syllabus content is only the basic aspects. If you study the basic aspects or if you understand the basic aspects, then you get the result. Then finally, Unit 5, it is only problem. Same problem you can work. And then same problems I will come up to case determination. That's all. The rest, of course, it is same, because same problem I will take. I will come up, I told you already the change. What is the difference between finite element approach and this? So that's only step 2, 3 is. So that I will indicate it in the finite element problems. That is same 3 types of problems, and I will close the subject. So next I will continue ಮಾಡೋಣ.